Hello and welcome to today's webinar. I'm glad that you had the opportunity to join us today. And just like probably every other webinar that you've been in, everyone's mic will be muted. However, you can participate in the conversation. If you'd like to place a chat and a question, we're going to be doing a time of question and answers at the end of the presentation. So feel free to do that if you have any questions. If you need any specific help as well, you can also request that we can do a demonstration for you on a more intimate one-on-one type of presentation to answer any type of specific thing that you may need. So if you'd want to do that, you can request that as well. And so thanks again today for joining us with our webinar on error proofing and 5 key assembly processes that we can use to help with the error proofing process during the assembly. So a little bit about Mountz. We've been in business since 1965, so we are in our 56th year of business. We have several different locations. We have our corporate office located in San Jose, along with our Western Service Center. We also have our distribution and warehouse facility located in Foley, Alabama. And we also have our international sales and service office located just outside of London, England. So our global presence is getting bigger, and that just goes along with some other firsts for us. We were the very first company to develop the electronic torque analyzer for the US military. We also are a 100% torque focused company. So we deal with products that either measure torque or apply torque or confirm torque. We just do torque products. So when you think of Mountz, it's very synonymous with torque. Our primary customer base is going to be our medical field, the biotech, aerospace and defense, the automotive and electronic industry makes up the majority of our customers. So my name is David Cash. I'm a member of the marketing team here at Mountz. I've been with the company for 15 years, and I've been in the torque business for 20 years as well. So I started out as a territory sales manager with Mountz, and I've held several positions throughout the company. So I do have a little bit of experience when it comes to error proofing. So you may hear the term error proofing. It comes from a Japanese methodology in manufacturing called poka-yoke, and it basically means to mistake proof an assembly process. And so you don't give the operator, in this case, the ability to accidentally make a mistake. We kind of program the behavior with the use of the tools that we were using and provide a clear and a demonstrated process that they must go through with the poka-yoke type of environment. So with that, we see these types of things in everyday use. So when we start our cars, the car must be in neutral or in park. When we use elevators or there's garage doors, they're built with sensors so that the doors don't close on people and that the elevators can function. We also see this when we're filling up our vehicles. The nozzle from the gas pump there will automatically shut off once the tank is full. It won't let the pump work unless it's fully engaged. So those are some items that we see with error proofing in everyday life. And so right now we're going to go ahead and institute our poll question for today. And right now, are you currently using any error proofing tools in your assembly process? And so we'll give you just a couple minutes here, or just a few seconds to go ahead and answer that question. And looks like we have some answers coming in. Awesome. So it is kind of split just a little bit skewed a little bit towards yes, that we are using some error proofing processes within the assembly. So thank you for participating in that. And so as we kind of jump into the error proofing as it relates to manufacturing, you know, we take a look at some of the risks of actually manufacturing parts and products that may be defective. There's a lot of costs that are involved in that, whether it be customers that will be returning product, either the end user or perhaps it's a sub-assembly for another company. There's a lot of financial and productivity waste there with either rework or downtime. And then the big issue of if you're working on an application that is safety critical, that if there is a failure that it could result in harm to someone or even possibly death. And so we want to make sure that we can help to eliminate that type of risk within the manufacturing process. And so a lot of this can come from human errors. And so what are some of the risks that are involved with that? Misunderstanding the process that is used for the assembly, the lack of experience or training for the operator. They could just be, you know, in essence, forgetfulness, just misunderstanding or misidentification of parts that are used, the lack of supervision or oversight, and if the operator gets interrupted or is delayed in their production. And so the human aspect can play a big part in the actual risk that is involved in the manufacturing errors that we may see. Some of the causes for the defects that we might see are going to be the procedures are not followed correctly. Also, the assembly process may have inherent errors within them. Components may have missing parts or not missing components. The process is incorrect when they're doing the work. They're not using the correct tightening procedure when doing the tightening, and they could be using the wrong tool for the specific application. And, you know, when we look at some of the common tightening failures associated with torque, obviously improper torque control is the biggest. Either it's over torquing the product or under torquing. Both of those can have significant failure risks. Cross thread events where the system is going to recognize that cross thread and torque out. We also have lifted or unfinished fasteners, and possible tool performance is using a tool that is not properly calibrated or is out of calibration. So a lot of these things are kind of the common failures. Obviously, there are others that can exacerbate any type of failure, but those are some of the common ones that we are dealing with. So when we take a look at some of the error proofing principles, we want to try to eliminate any errors that we can. We obviously want to try to prevent any type of problems that may come during the assembly. If we can replace a specific tool with more error proofing features, that's always a good thing. If we can automate the procedure so we can link certain items within a workflow, that's going to help in the error proofing process. If we can detect errors and fix them on the spot, again, another help in the error proofing process and helping to minimize any type of effect that may come from other errors within the system. And so we can take these specific principles and we can go ahead and we can apply them to the torquing and application for assembly. And so from the 5 techniques that we can use here, and this is related to our DC tool line, and we'll talk a little bit about that and show you how we can use these particular principles within the programming of the certain tools. But we want to ensure that there's proper torque control. We want to make sure that the process control that we have in place is solid, is valid. We can then create assembly procedures within that process control. Part of that would be screw counting. We want to make sure that every fastener gets done. We have our job manager, and we want to be able to monitor the procedure as things are happening in real time. And so we could kind of dive into each one of these as well. So when we talk about ensuring the proper torque values, we want to make sure that we can program those specific values that we need. We can apply tolerances to those values. We can program RPM and speed. We can also help to eliminate any type of operator influence that may be coming. And we want to, again, be able to detect any fastening errors within the torquing process. The process control, we want to be able to set up multiple fastening tasks within an assembly process. This is going to be able to help us decrease the number of tools that may be needed at a workbench. We then can help, again, assembly sequencing within those programs. And because of the fact that we can use different presets and values, it may be able to minimize the number of workstations that are needed. And in the entire process control, we can reduce the amount of inspection that is needed if we can put these specific controls in place. So screw counting, again, this ensures that all the fasteners for a specific assembly are done. We do have the ability to also detect when there is a fastening error. That will not be counted until we get a good result. This is going to help to prevent any type of miscount. And we can also then do some job cycle counting as well, where we can track the number of cycles. With our job manager, this helps us to be able to create a process control. We have an interface that will allow us to do improve on training, help us provide a visual guide. And this is oriented around our EPT product, which is our battery transducerized DC control system. And I'll show you what that looks like here when we jump into the demo portion of the presentation. And then finally, we have real-time monitoring. So we do have built-in transducers into our ECT and our EPT products. This is going to allow us to record all of the torque and fastening data that is happening. We also have the ability to interface with line control through the inputs and outputs. And then we also have error notification as well. So all of these functionalities within the entire assembly process can really help us move from a state where we don't have as much control with our assembly to where we can really kind of hone in and make that process much better and kind of fashion the behavior of the operators into allowing us to be able to make sure we can error-proof that particular process within the assembly. And so let's go ahead and we can jump into the demo portion of this. I've got 2 systems with me that we're going to be able to take a look at. First is going to be the EPT battery DC control tools. As I mentioned, we'll take a look at that when we look at the job manager function. And then we also have our EC and ECT DC corded version. And we'll be looking mostly with this unit, but the really great thing about our DC tool line, whether it be the EC and ECT that we're dealing with our corded version, the EPT version, which is our battery DC system, or whether it's our ADC series, which is our automation and robotic tools, all of the way that we program these tools are very, very similar. They all use the same type of language and verbiage and settings. So it makes it very easy to be able to go from one system to another system without too much of a huge learning curve in there. So let's go ahead and take a look at the, when we want to ensure the proper torque for us. And so I have here our controller for our ECT product. And right now we're currently using preset number 1. We have a target torque at 1 Newton meter. And then we also have some other values down here that are pertaining to the actual rundowns that may happen. And so in this case, we want to ensure that we're properly setting the torque for our specific application. And for us to do that, we can simply log into the controller. We can go to our parameter function and we go to our fastening tab. And so in here we have 15 of our presets. Right now we're dealing with preset number 1. If we wanted to change to a different preset, we can just come in here and select which preset we want to look at and do that. But in this case, we just want to program what our preset torque value is. And currently we're at 1 Newton meter. So I'm just going to go ahead and change that to 1.25. And now we've updated that particular preset. And so one of the other things that we can do to ensure that we have our proper torque is we can put in a target limit percentage. So if we have a target that we need to make sure that we are staying within. So right now, currently I have it set at 10%, but we can change that to 6% or 5% or 15%. If we don't want to use that at all, we can set it to 0. But in this case, I'll just leave it at 10%. And then we have some other values that we can look at. But one of the things that really us to be able to ensure that we have the proper rundown and proper torque on our system is we have the ability to use a tightening strategy where we have torque control with angle monitoring. And the angle monitoring allows us to be able to clock the amount of turn that happens with a fastener. And so on a typical rundown, if it takes, say, for example, 2,000 degrees of rotation for us to fully seat that fastener, we can create a window that is going to be acceptable for us to see if that certainly happened. And so we have down here, we have our minimum and our maximum angle that we can apply to this preset. So if I come in and set the minimum angle at say 1900 degrees, and I set our maximum angle at 2200 degrees. So now the system is going to not only look for our target torque at 1.25 Newton meters, it's also when we do reach that value, we must be within these angle windows as well. So this can be done with either using the min or the max or in combination of both that we're doing here. And so there is one additional error that we can stop and see. Because we're monitoring angle, we want to make sure that the operator holds the trigger down for the entire rundown until the system torques. And so with that, we can go to our controller and we can do what we, or implement basically what is our fastening stop error. And with this, this will allow us, if there is a release of the trigger before the tool actually runs down, then we can cause the system to give us an error, and it will give us that non-torque up error with that. And so let's see here, if I come back here. So we have our fastening OK signal and our judgment. Let me make sure I'm just not missing it on this page here. So the controller menu allows us to be able to tell the system how it is functioning with the different items that we have on here. And so I did have it set here. And if we carousel back around, I apologize. I am just overlooking it here. Fastening stop error here. So if I turn this on and we come back out all the way to our operations screen, if I go ahead and I run the tool, so we have our fasteners down here. I run the tool and let go before we torque, we receive a no torque complete error. So if I go ahead and run the fastener down, sorry here. And so again, we need to make sure that we're within the 2000 degrees of rotation. And we were. So if you can see here, we have our angle of 1980 degrees, actually 1986 as our angle. And so we did meet that requirement for our angle to go ahead and be satisfied. If we want to basically see what an error would look like if we did not meet that, so I'll just pull this fastener back up just a little bit and run it back down. And now we have reached a minimum angle error. And so this could demonstrate what would happen if there was a cross thread type of an event. We would certainly reach the torque right at the very beginning, but there would not have been the amount of turn that fastener normally sees to make sure that that is a good and acceptable rundown, and that can be counted for that particular preset. So with that, that is how we can do that to ensure that we have the proper torque for a specific preset or fastener. And so now when we look at process control, what we can do is we can program multiple presets that would allow us to be able to program a fastening sequence. So to do that, we can, again, log into our system. And we can go to what is our model function. And so the model function basically allows us to create an assembly process within a cell type of build or environment. And so we can say that we have 20 different steps that we can add for one specific model. And one model can be made up of 15 different preset values that we have stored in the controller. So in this case, we'll just make a very simple model. We're going to do a fastening step. And we're going to use preset number 1. And we're going to do that for one fastener just to make it easy for the demonstration here. Okay, 2 fasteners. So after we've completed 2 of those rundowns, we then can move to another fastening step. And in this case, we'll use preset number 2. And we'll use that for 2. And then finally, we'll do another fastening on preset number 3. And again for 2 fasteners. And so now what is going to happen when we run this model is for the different fastening steps that we have, once we've completed our fastenings with preset number 1. After 2 fastenings, the system is automatically going to change to preset number 2, and so on throughout the model. And so if we go ahead and run this, there's one other thing that I need to do here, and that is just change the controller into the model selection mode. And this brings us out of the preset mode and into the model. And so right now you can see that we're using model number 1. We are using preset number 1, and this is step 1 of fastening. And so we can go ahead and run this down for our 2 fastenings. And now you can see that the model has changed and updated. We're now still on model 1, but now we're using preset 2, and we're now in step 2 of the fastening. So I can run an additional 2 at preset number 2. And now we've moved on to step 3, which again is using preset number 3. And again, if I let go of the trigger, we are still monitoring for our angle requirements with the different presets. And so now our model is complete, and the system will go ahead and reset for the next model. There are some other process things that we can control at this point as well, but right now it's set to go ahead and reset, and we're back to preset number 1, step 1 in our fastening. So that's how we can use the process control. With our screw counting function, we just basically saw how we can do that with our model function, but we also have the ability to use the screw counting as a global type of setting. If the tool is not being used in the model mode, we can have a global setting where we have down here, we have a count, which is 2 of 2 at this point, but that was in conjunction with the model. But if we come into our screw count menu here in our parameters tab, we can come in and we can declare what is going to be the global count for a specific type of fastening. Again, not using the models, but if there is communication with line control and a PLC, we do have the ability to send out signals to that line control, either with a middle point or a completion point to allow the conveyor or some other process control equipment to move on. So that is how we could do that with a global type of setting with our screw count. And so we kind of saw that again with our model function, where we have our count down here. If we did not receive a good rundown event, then that fastener is not counted. The operator does have the opportunity to redo that particular fastener, or it can be rejected based off of whatever internal process you may have in regards to that. Next is going to be the job manager. And so with the job manager, I'm going to go ahead and make one adjustment here with the camera and tool. And this is going to be our display for our EPT tools, and just make an adjustment to the focus. And there we go. And so again, the job manager allows us to be able to program an entire assembly. So this is kind of piggybacks on what we just did with the model function. On this particular tool in our job manager, we're able to also provide the program functions for a specific assembly. And then we can also do the, let me just jump back here. We can also do some visual guidance and also put target data in that as well. And so in here, if I go into our job manager, I've basically already logged into the system. I've got a couple tools that are connected here, but I'll just select the webinar in February here, and we're going to go ahead and edit this particular job. And so we've got a couple different things that we can do here. We can add a fastening step. We can do inputs and outputs, so we can have communication within the process. We can do a delay, and we can do a message. And so right now I've got 3 steps in here. The first is, you'll see we have, please use this particular tool, the 005 P tool. If the operator is using multiple tools connected to one controller, that is fine. Only the tool that is selected in the fastening step is going to work. So if they picked up the wrong tool, they would not be able to use it. So in this case, we can display this message on the screen for 3 seconds. And we're going to go ahead and do a fastening here using this particular tool. We're going to do 2 different fasteners, and we're going to use preset number 1. And now we also have the ability to add an image of the application and part. And if I go ahead and tap on the image, we now have the ability to add target data for that particular assembly. And so right now I'm currently using fastener 1. And if I needed to change the location for this, let's say this should be the fastening location, I can just simply drag it to that location. I can fine tune it by using these arrows if I wanted to. We can change the actual thickness of the target here. And I can change the radius. We can also change the colors. If we get a good fastening, it's going to turn it green. If we had a no good fastening, it would turn it red. And so this is for fastener 1. And so if I tap over to fastener 2, you can see that we don't see it. It's actually on this side of the screen. So we can move the menu over. And now you can see this is fastener 2. If we wanted to adjust that, we can then go ahead and move that to the right location. And if we want to go ahead and just minimize the menu altogether, you can kind of take a look and see a specific process for that rundown. If we want to, let's go ahead and go show the menu back here, and we'll select OK. We can go ahead and we can add another message here, and we can then select from our images here. If we want to go ahead and use, let's say we're going to use the right angle tool for this next portion of the build, we can select that. We're going to have a delay. Again, we can set it for 3 seconds. We could also use some other means to move that message. And then we're going to fasten. Again, we'll use this tool. We'll do it for a series of 3 fasteners at preset number 1. And then we can come in and load the image. And now we can add our target data. So this is fastener number 1, fastener number 2. Excuse me, I did change that. And let's move this back over, and we'll make this number 2 now. There. And then we'll move on to fastener number 3. For this one, let's go ahead and change the radius. and the width of that. And we'll also change the color. Let's make this more of a blue color. We can also go ahead and put in the hex code, or in this case, the RGB codes for a specific color if we wanted to. And now we have that down here. We can hit OK. And let's go ahead and save this. And now we can come out and we can go ahead and run this particular job. So we have our message. Now it's giving us our target data for where we need to go on the assembly to do the fastening. The really nice thing about this controller as well is that we do have an HDMI out. So if we wanted to mirror this onto a larger display, we can do that. If I go ahead and do the process of the actual fastening, you can see now we've got our two good values using our pistol grip tool. Then we'll move to our right angle tool. And now we have a job complete, and then it recycles and starts again at the beginning. So this is a really good way that we can have again, a visual, and also this helps for training and allowing the tools that are being used for a specific step are the only ones that are available with the battery function tool. So if we look at our real-time monitoring functions, this gives us the ability to have data sent directly from the controller to a couple different places. So within the controller itself, we have an SD card where we can tell the system to write all of the torque and fastening data to the SD card. That SD card can be removed and downloaded, and we can gather the information that way. We also have the ability to stream the data out via the RS-232 port or the Ethernet port. Those can be sent to an internal MES system through Modbus or Open Protocol. So we have a number of different ways that we can collect the real-time data for us. And we also have our inputs and output settings. So let's just go ahead and jump into, again, our menu in our parameter menu. And in our controller, we have our different menus. And within that, we have the ability to turn on the auto data. And so right here, we have our auto data output. We can go ahead and turn that on. And currently right now, this is set to the RS-232 port. We can also turn on our SD card as well, and any torque data then that we go ahead and run, we're going to be able to capture the time, the date, the preset that was used, the preset target, the actual torque that was delivered, the total amount of angle, also the total amount of time in milliseconds. If there was a fastening error, we would be able to get that information. If there is a preset change, we'll see that information. If there is a change in direction on the drive, we will see that information as well. So that gives us the ability to capture the data that's happening in real time. Again, if there is any type of fastening error, we'll be able to detect that, be able to rectify it and move on without creating additional problems for that assembly down the line. We also have the ability to use our input and output settings to be able to communicate with line control for our PLC communication. That's done, again, through our parameter menu in our IOs. And so All of the inputs and outputs are digitally assignable. So we just need to know what pin configuration we want to use. If we want to change a specific value, we have a number of different input and output selections that we can use for a specific communication that may be needed for any type of monitoring with a line control that may be used here. And so with that, we're going to go ahead and jump to our questions and answers if anyone has them currently. I believe Chris Morris, our marketing manager, is gathering those questions, and we can go ahead and take a look at any of those that you currently have. Chris, do we have any questions?
Yeah, Dave, here's a few starter questions to kick off, and thanks for the demonstration. First one, can you explain what's the difference between a transducerized and a non-transducerized tool again?
So we do have two different types of current control products. Our EC is a current control system, and then we have our ECT, which is a transducerized DC system. And so the difference is with the ECT, we have a built-in transducer that is monitoring the torque as the tool is being used. So we have a process, a closed loop with that particular style of transducerized tool that is going to allow us to be able to monitor the torque that way. With our current control version, that torque is monitored by conversion from current to torque that is generated from its torque calibration and that slope that is generated throughout the range of a specific tool.
All right, Dave, thanks. Next question is, what is prevailing torque, and how can it be? Can your system be used for that type of application?
So there's a couple different scenarios in when you're dealing with prevailing torque. One would be if you are using a security type of patch or thread locker, or you're running through another type of security feature where the actual cutting of that particular patch or thread is going to be generating more torque than you would see at a final seating torque for that particular fastener. And so with our system, you can tell it to basically ignore the higher torque value for a certain period of time. When the unit sees a drop in that particular cutting torque, then it will go ahead and look for the final torque. So that is one way that we're dealing with the prevailing torque. Another example is if someone is wanting to monitor the prevailing torque, take an additional amount of torque or a preset to that and add it on top of that. Currently, our system does not do that. However, there are a couple different things that we can use through the monitoring function to help us to kind of better see what that might be. But that is something that, that we're trying to work through at the moment for this particular type of prevailing torque assembly.
Okay, thanks, Dave. Next question, can the system be used for thread tapping applications?
Thread tapping, you can certainly do that. We can use a couple of different methods to be able to do that. We have, as I mentioned, with our programming and our torque profile strategies, we can employ a angle control with torque monitoring. So we can cut threads to a certain angle. We can then go ahead and back that fastener out and then run it back down to a seating torque. That can be accomplished with our multi-sequence process that can handle stacking different presets on top of each other into one trigger pull event. So there are ways that we can do the thread tapping for sure.
All right, Dave, that was the end of the questions then. Thank you.
All right. I want to say thanks very much for joining us today. If you have any questions that you'd like to see something, again, a little bit more in depth, we can certainly do that. You can contact our any one of our technical support specialists or customer service representatives, and we can move to do that for you. So thanks very much for your participation today and your time, and look forward to seeing you at our next webinar next month. Thanks so much. Have a good day.